To my YouTube channel. So in today's video we will solve this Leetcode problem, find eventual safe states. So before we move on, let us first understand the problem statement. So in the question we are given a terminal node. So a terminal node is a node with 0 outgoing edges. So if I consider the example of this graph, here 1 and 6 are terminal nodes because both of them have 0 outgoing edges. If I consider 1, there is no outgoing edge from 1, and if I consider 6, there is no outgoing edge from 6. Hence 1 and 6 are terminal nodes. And let us understand what is a safe node. Okay? A safe node is the one that all the paths from that node leads to a terminal node. So let us understand, let us find out all the safe nodes in this graph. So for example, if I consider 3, so first we will find out all the paths that are starting from the node 3. So 3 has only one outgoing edge and that leads to 1. And 1 is a terminal node. Therefore, we can say that 3 is a safe node. And if I consider 2, so 2 has one outgoing edge. So we can say 2 has one path. Okay. So from 2 we can move to 5, and from 5 we can move to 4, and 4 we again move back to 2. So if a path starts from 2, it does not lead to a terminal node. Okay, therefore we can say 2 is not a safe node. So if I consider 4, so 4 has one outgoing edge. So from 4 we can move to 2. From 2 we can move to 5, and from 5 we can move back to 4. So hence we can say that every path starting from 4 does not lead to a terminal node. So 4 is also not a safe node. So if I consider 5, from 5 we can move to 4, from 4 we can move to 2, and from 2 we again move back to 5. So all the paths which starts from node 5 do not lead to a terminal node. So 5 is also not a safe node. And if I consider node 7, so it has one path. Okay, from 7 we can move to 5. Okay, so 5 has 2 outgoing edges, so there will be 2 separate paths. So let us first move to node 3. From 5 we can move to node 3, and from 3 we can move to 1. So after starting from 7 we can move to 1. So this path starting from 7 leads to a terminal node. So this path is safe. But let us explore the second path which can start from 7. So that would be from 7 we can move to 5. From 5 we can move to 4. From 4 we can move to 2. From 2 we again move back to node 5. So 7 has 2 paths, and one of them leads to a terminal node and the second one does not lead to a terminal node. which conveys that 7 is also not a safe node because not all the paths leads to a terminal node. So we only have, so 0 is also left. So if I consider 0, 0 has only one path and that leads to 1, which is a terminal node. Hence 0 is also a safe node. So we only have 0, 1, 3 and 6 as safe nodes, and 2, 4, 5, 7, all of them are not safe nodes. So we can conclude that all the nodes that are part of a cycle in a graph are not safe nodes. So nodes that are part of a cycle are not safe. So as you can clearly see in the graph, there is a cycle in the graph. From 5 we can move to 4, from 4 we can move to 2, and from 2 we can move to 5. So 2, 4 and 5 are not safe because they create a cycle in the graph. They are part of a cycle in the graph. And another point that we can conclude is a node which connects to a cyclic node is also not a safe node. If we consider 7, 7 is not part of cycle in the graph, but it is connected with 5, which is a cyclic node in the graph, which forms a cycle in the graph. Hence, 7 is also not a safe node. Okay. So before we move on, let us first revise what is topological sort. So toposort is linear ordering of vertices in the graph such that for every directed edge from U to V, U always appears before V in that particular order. And we all know that topological sort only exists for directed acyclic graph, which means if a graph contains a cycle and we use Kahn's algorithm to find the topological order, then a final topological order will only consist of those nodes that are not part of cycle in the graph, or and it will also exclude those nodes which are connected to a cyclic node in the graph, which means the Kahn's algorithm excludes all those nodes in a final topological order that forms a cycle in the graph, or the nodes which are connected to a cyclic node in the graph. Therefore, we can use Kahn's algorithm to find the eventual safe nodes in a graph. Okay. Okay, so in order to find out the eventual safe states, first we will list down all the terminal nodes. So we have two terminal nodes, 1 and 6. Then for all of the terminal nodes, we will write down all the paths via which we can reach these terminal nodes. Okay. So one path is we can reach to 1 via 7, 5, 3, 1. Another path is 0, 1. Okay. And another path could be 4, 3, 1. Another path could be 2, 5, 3, 1. So what we can do is we will simply backtrack from the terminal node, that is 1, and while backtracking we will check for each node in the path if it is a safe node or not. Okay, so how can we check if a node is a safe node or not? By simply checking if all the nodes starting from the current path or current node leads to a terminal node or not. So we will simply backtrack from the terminal nodes or dead ends to see if we can reach safely from the terminal node or not. So if I consider this path 7, 5, 3 and 1, okay, if I backtrack from 1, so as we have already understood that all the paths starting from node 3 leads to a terminal nodes, so we can say 3 is a safe node and we can consider 3 in our answer vector. And if we move back to 5, so as we know that all the paths starting from 5 does not lead to a terminal node, therefore we can say 5 is not a safe node, hence we will not push 5 in answer vector. And now we will backtrack to 7, as we already know that all the paths starting from 7 does not lead to a terminal node, so we will not push 7 inside the answer vector, we will only push 3. And if I consider the second path, that is we can move to 1 from 0, and if we backtrack, so as we know all the paths starting from 0 leads to a terminal node, therefore we can say 0 is also a safe node and we will push it inside our answer vector. Similarly, if I consider this path and I will backtrack, so we know 3 is our answer, 3 is a safe node, so yes, it is a safe node. And if we move back to 4, we know it is not a safe node. Okay, so if we look at the graph, there is a way via which we can reach from 3 to 1, because this is the direction of directed edge, but there is no way we can reach from 1 to 3. So it would not be possible for us to backtrack in reverse direction. So in order to backtrack, what we can do is we will reverse the edges in our graph. So when we reverse the edges in our graph, the in degree and out degree for a node will be swapped. Let me give you an example. So if we consider this graph, the in degree of 7 is 2 because it has 2 incoming edges, and out degree is 1 because it has 1 outgoing edge. And if I reverse the edges in this graph, now the in degree will become 1 and out degree will become 2. So if I reverse the edges in my graph, then then the in degree of outgoing then the in degree of terminal nodes will become 0, because the out degree for terminal nodes is 0. And if I reverse the edges in my graph, the in degree for terminal nodes will become 0. Let me explain you by redrawing our graph. If I reverse the edges in my graph, okay, so now the in degree of 1 is 0 and in degree of 6 is also 0. What we can do is we will simply push 1 and 0 inside a queue. Okay, now we will pop the front element from the queue and we will process its adjacent nodes. So now since we have popped the first element from a queue, we will remove the outgoing edges from 1 and will reduce the in degree of its adjacent nodes by 1. So as of now, the in degree of 3 was 1 and the in degree of 0 was also 1, and after reducing the in degree by 1, the in degree of 3 and 0 both become 1. So we can simply push both 0 and 3 inside the queue. Okay, so as of now our answer consists of 1. Okay, now we will pop next element from the queue and push it inside our answer, 6. So I will pop out 6 and 6 does not have any adjacent edges. So we will simply move on to the next element in our queue. So the next element in our queue is 3. Hence, we will push 3 in our answer vector and will process its adjacent nodes. So 3 has two adjacent nodes, 5 and 4. So first, we will remove outgoing edges from 3. Okay. Now, the in degree of 5 is still 1 and the in degree of 4 is still 1. So we need not to push anything inside our queue, and hence we will simply move on to the next element in our queue. So the next element in our queue is 0. So if I consider 0, so it does not has any adjacent nodes. It doesn't have any adjacent nodes, so which means we have done all the work for 0. So we will simply move on to the next element in our queue, and after popping out 0, we can see that our queue has become empty. Therefore, our final answer consists of all the eventual safe nodes, and as we all know, we need to return the answer in sorted order. We will use the sort function to return the eventual safe states. As you can see, the Kahn's algorithm has excluded all the nodes that forms a cycle, and it has excluded 7 also, because 7 was connected to a node which does not lead to a terminal node. Okay. So 7 was connected to 5, and all the paths starting from 5 do not lead to a terminal node. That's why Kahn's algorithm also excluded 7 from the answer. Now let us understand the code. So here we are given a graph, which means the adjacency list for a graph, and so in order to perform Kahn's algorithm, we need to reverse the edges in our graph. So what I am doing is I have created a reverse adjacency list. Okay. So after that, I will iterate over my current adjacency list and current graph, and here I have reversed the edges in my graph. For example, if for example, if I consider this, here the zeroth element of graph indicates that from 0 we can navigate to 1 and 2, and since we need to reverse the edges in our graph, we need to convey that from 1 we can reach to 0 and from 2 we can reach to 0. So here I am iterating over the adjacency list for 0th element, and here I'm simply reversing the edges, and for the adjacent elements of 0 I'm simply increasing its in degree. Now, so first I need to push all those nodes with 0 in degree in a queue data structure. So now I will iterate over my queue and pop out front element. And will push the current node in our answer. Now I will iterate over the adjacency list for the current node and will reduce the in degree of the adjacent node by 1, and at any point if the in degree of adjacent nodes becomes equivalent to 0, I will simply push it inside the queue. After coming out of the queue, I will simply sort my answer. And return it. Oops. So yes, thank you so much everyone for watching my